Okay, in this video, I want to discuss the domain and range of a function. The remarks I'm going to make here would also apply to uh, general, not just functions, but general relations as well. Okay, but let's take a quick look here. Domain and range, some definitions. So this is from section 3.2 in OpenStack's textbook for college algebra. Okay, the domain of a function is the set of all possible inputs of the function. Okay, the range is the set of all possible outputs of a function. Okay, so the domain, you think of the set of all inputs. Okay, range, the set of all outputs of a function. Now, in the case where the function is given explicitly, either by a set of ordered pairs, like I've written here, or by an arrow diagram, also known as a map, like I've drawn here. Okay, so these are the same function here. You can see just drawn in different ways. Remember, in an arrow diagram, you've got, well, domain elements always pointing at range elements. Okay, so don't forget your little arrowheads on your arrows there. Anyway, so I've got a function defined this way: 1, 2, 4, 7, 5, 11, 6, 23. What is the domain of the function? Okay, well, the domain of the function I like to often write this way: a script D with a subscript representing the function. So here I've got script D, subscript F, so that I'm looking at the domain of F. Okay, so that notation, you know what that means, and that's the domain of F, and that would be the set of all first elements here. Okay, it's really easy to see if I use the arrow diagram here, or map. Some people like that term. You can see it's just the set of all the first elements in the ordered pairs. Okay, that's another way to think of it, just the set of all first elements from all the ordered pairs. And you see that's 1, 4, 5, 6 in any case. Okay, so this is just a set here. So I've got my curly brackets, that are braces, if you like that word better. Okay, the range of F is the set of all second elements in each of the ordered pairs here. So all these elements that are being pointed at. Again, this stuff would apply to a general relation also. But this would be then what? 2, 7, 11, 23. So notice that my notation here for range, I guess I didn't mention that, that's a script R with a subscript F. So range of F. And that's so the set 2, 7, 11, 23 for this particular function. Okay, so you can see finding the domain and range when a function is given explicitly like this in terms of ordered pair or as an arrow diagram is very, very simple. You've got 1, 4, 5, 6 as possible inputs, right? 2, 7, 11, 23 as possible outputs. So you've got this domain and this range, okay? All right, suppose that the function is a real function given by a graph in the xy plane. Like this I've drawn it. It's a little sloppy here, but I think you'll understand what I mean. Okay, so I've got this is a function, right? Okay, passes the vertical line test. To each x there corresponds exactly 1 y. Okay, if you haven't studied that yet, make sure you understand that in the book. Okay, anyway, what is the set of possible inputs? Well, you could think of all these points in the plane as being ordered pairs, right? For example, this ordered pair right here is what? X is 2 and y is also 2. Okay, so obviously we have what? An element 2 in the domain and also in the range, as a matter of fact. Both have that element 2 there. Okay. To find the set of all possible inputs, that's the set of all possible x values, or whatever you're calling the horizontal axis, okay? We usually think of that as the independent variable, and the vertical axis, often written y, as the dependent variable. Okay, so here's what you want to do. The domain of f is found by taking the graph and projecting it up or down, depending on where it's located, onto the horizontal axis, okay? So that means take every point here and just project them straight on down, okay? Project every single point there straight down. Okay, it looks like I'm bending my arrows a little bit. Okay, but if you did that, project all the points that lie on that graph onto the x-axis, the horizontal axis here, this point would be open right there at -1, but I would get what? All these values of x, okay, projecting it on there, all the way out here up to and including 2. Okay, so I've written that here. D subscript f equals the set of all x such that x is between -1 and 2, and we're including 2 here, but not -1, as you see. So this would be what? In interval notation, parentheses, -1 comma 2 square brackets. Okay, alrighty. So that's how you're going to find the domain of f graphically. Okay, so in the ordered pairs, making up, this is an infinite set of ordered pairs up here, right? You've got all these ordered pairs, x, y. You're picking off all possible x values, okay, by projecting those points onto the horizontal or x-axis, okay? How would you get the range graphically? Well, the range of f is going to be found by projecting the graph left or right, depending, onto the vertical axis, okay? So you're looking at y values here. So if I was to take all these points on the graph now and project them horizontally, left or right, whichever is required, onto the horizontal, or the vertical axis, I'm sorry, do you see, I would get everything from what? 1 up to 2, okay, so I would get 2. Notice I wouldn't actually get 1 here, though. That would be an open dot, because this is actually what? Open right there. That's actually the point -1 comma 1. Okay, so that's not an interval. Those are coordinates. -1 comma 1 here. So the y-coordinate of that open point is 1. If I project that open point onto the y-axis, I would still get an open point, but the y value would be 1. So notice I get everything when I'm projecting all these points on here. I would be projecting on to the y-axis so that I get everything from 1 up to 2, only you wouldn't actually get 1, but you would get 2 because this is a solid point right there, isn't it? So it'd be everything between -1 and 2, or not -1 and 2, 1 and 2, but you would not be including the 1 there. So you see, I've got 1 is less than y is less than or equal to 2. Okay, in interval notation, that would be parentheses 1 comma 2 square brackets. So that would be the way you would find the domain and range from a graph, okay? From a graph in the xy plane. Okay, how about on this one? Can you decide what this is? Hopefully my drawing isn't too sloppy here. The domain and range of y equals g of x here, okay? So I've called this graph y equals g of x. So what you would do is what? Mentally project this graph onto the x-axis to find the domain, and you would project it onto the y-axis to find the range. If I project all the points on this graph onto the x-axis, I think you can see I would get everything from -2 out to 0, okay? That would be solid at 0 here, but it would be open at the left-hand end, so there would be open -2. And then when I project this little chunk of the graph onto the x-axis, because both those endpoints are solid, it looks like I would get everything between 1 and 2 inclusive. Okay, so I would shade that in. So that would be my range, or my domain. Everything from -2 to 0, union 1 to 2. Okay, so -2 is less than x is less than or equal to 0. Okay, or x is between 1 and 2 inclusive. So in interval notation, we would have from what? Parentheses, -2 comma 0 square bracket, union 1 to 2. Okay, alrighty. How about for the range? Okay, how about for the range, I'd take a different color. That would be a good idea. Let's do that in blue here. Oops, it changed that last part. Let's change it back here. Okay. Let's go to that. And that's a different color still. Okay. That. Okay. This is kind of a silly system, so I'll go like that over there. And I'll go blue. There we go. Okay, how would we get the range? Okay, instead project the graph onto the y-axis. And you can see I would now have what, an open dot here. Okay. And projecting all these sideways onto the horizontal, I would get everything from 0 up to and including, it looks like 4 up there. Okay. Okay. So that would be solid. So from 0 to 4. On the other hand, since these are also solid, and I project these onto the y-axis, it looks like I get everything from -3 to -2 inclusive, like that. So I'll put in solid dots. Okay, so you can see the range and the domain written clearly there, hopefully. Okay, so we would say everything from 0 to 4, okay, including 4 but not 0, or between -2 and, that's wrong, I wrote that wrong, -3 and -2 inclusive, so that would be a -2. Okay, what a faux pas. Okay, -3 to -2 here. Sorry about that. Okay, this would be the more reasonable way of writing it then. Right, the smaller numbers to the left and the larger numbers to the right. So we'll go from -3 to -2, union 0 to 4. Okay, so the way I've drawn it up there, I'm just saying I drew this one first and then this one. But the way we like to write things, I wrote this one first and then this one in interval notation. Okay, alrighty, so let's keep going here. Let's maybe do the range first on this one. Okay, so you would take all the points that lie on y equals x squared, and you're going to project every single point onto the y-axis. Okay, this point is already on the y-axis. It's also on the x-axis, but that projects right onto itself. Okay, do you see I would get every value of y from 0, okay, because obviously this is the origin right there, right? 0 to infinity. There would be no limit this direction. That's indicated by these arrows sort of here. You guys know what y equals x squared looks like. That's sort of our quintessential parabola. Okay, so the range would be from 0 to infinity there. Okay. All right. How about the domain? Okay, which we usually find first, but not this time. You say I would just do what? Project every single point onto the x-axis. And again, that goes through the origin, so that's projected onto itself. Okay, and do that for every single point. Do you see I would get, what I end up with is all real numbers. I would get the entire real number line, the x-axis, covered this way. Okay, so this whole thing gets shaded in. Okay, a little sloppy here. But the domain is all real numbers then, is another way of saying it. It's from -infinity to infinity. Okay, all real numbers. Alrighty, so you should be able to do some problems in the textbook that way. Just look at them graphically and think of this projection idea. Now let's come back here. Let's talk about the domain range of real functions given by formula. Okay, now the first thing I'm going to say here, for now we're not really going to be looking at the range very much. Okay, functions given by formula. Those can be trickier, okay, but the domain should be somewhat easier. Let's go ahead and look at the definition. It's actually the same definition we had before. This is sometimes called implicit domain too. Okay, so if you just give a function by formula, then we assume that its implicit domain is the set of all real numbers for which the formula makes sense, okay? In other words, it's as wide as possible. So we use the widest possible interpretation. Okay, so I write that here. If a function f of x is given by a formula with no further stipulations, okay, so you don't restrict the x value or whatever the independent variable is, the domain d of f is the set of all real numbers, for which the formula yields a real value. Okay? Some people would say which makes sense in the real numbers. Okay? But essentially this is saying the formula has to yield a real value. Let's look at some examples. Okay? Say y equals f of x is 1 over x minus 3. Okay? I didn't say anything else about this function. I just gave a formula for it. Okay? No further stipulations here. Okay? This formula yields a real value for all real values of x except 1. X equals 3. If I try to let x equal 3 in here, I would be going 1 over 3 minus 3 is 1 over 0. That doesn't make any sense, does it? Okay? But notice that I could put any other real value in here, and it would be fine, wouldn't it? Okay? All right? Any other real number value you could stick in here, it would make perfect sense in the real numbers. So the domain is the set of all x such that x is not equal to 3. So you've taken the real numbers and you've kicked 3 out, but retained all the other real numbers. So that would be from what? In interval notation, from minus infinity to 3, parentheses, union, parentheses, 3 to infinity. Those are all real numbers except 3. Okay? How about y equals g of x is the square root of x? Remember, we're only concerned with real numbers here. Okay? This formula yields a real value whenever x is greater than or equal to 0. Don't forget that the square root of 0 is 0. It still exists as a real number. So what do we have then? So the domain of g would be all real numbers greater than or equal to 0. In interval notation, that would be square bracket, 0, comma, infinity, parentheses. Okay? All right, so jumping to it here without using the set builder notation. How about this one? Y equals h of x equals x squared. Okay, we actually looked at the graph of that just a little earlier here. This formula yields a real value whenever x is a real number. So the domain is all real numbers. So how do we write that in interval notation? You remember parentheses, minus infinity, comma, infinity, parentheses. Okay? You can see the range that we did have the range up there earlier. It's from 0 to infinity, including 0. Okay? But here, like I stated, I'm going to be focusing strictly on domains for now. Like I said, ranges are going to be a little more complicated here. Okay, let's do another one here. Let's say y equals k of x is x over x squared minus 9. Now, some people would call this a rational function. A rational function is a ratio of two polynomials. Now, let me say right now, the implicit domain of any polynomial is all real numbers. For example, if I was to forget everything except x squared minus 9, the domain of x squared minus 9 is all real numbers. I can take any real value of x and evaluate x squared minus 9, and I won't have any problems. I'll get a real answer, right? Okay, likewise the numerator. The numerator is a polynomial. It's just plain old x. I can quote-unquote evaluate that at any value of x also. Its domain would be all real numbers. But when you're dealing with a rational function, which is a ratio of two polynomials, there is one problem that can occur, but only one problem can occur. Okay, the domain and the range exist for all real values of x, but there's one other problem that can occur besides the non-existence of the domain or range. That is what? Oops, you might be dividing by 0. But so long as you're doing that, you should be fine. Nothing else can go wrong with a rational function, a ratio of polynomials, except possibly that the denominator might become 0. So here's what we're going to do. As soon as I see that's a rational function, right, I know the domain's going to be all real numbers except where the denominator is 0. Okay? So I've written that here. What I'm going to do, my strategy, is to take the denominator, set it to 0, and solve for x, and then kick those numbers out of the real numbers. What I'm left with will be my domain. Okay? Now, solving x squared minus 9 equals 0, you can just eyeball that in. You see that x equals 3 or negative 3. Okay? Such that the domain then is what? The set of all x such that x is not equal to negative 3 and not equal to 3. Okay? So the x has to satisfy both of these conditions. So it's an and statement. But anyways, you can see this is just the real number line with negative 3 and 3 booted out of it. Okay? So that is in fact the domain of this rational function. Okay, well, I hope you understood that. We shall continue with something called piecewise defined functions next.